Hey, John here. Time for an update on the FPGA code that I've been working on for the Z80 Nouveau project. A big thanks to everybody that supports this channel, especially the VIP patrons listed here. If you'd like to join the club, see the link below in the description on YouTube.
Nothing really changed with the FPGA board or the S180 board and the Pi and the arrangement, how I programmed that. We've talked about that before. What has changed a little bit is I added another 3 bits to the DAC logic, the all resistor DAC that I use to convert the now 6-bit color values to analog values that drive the VGA screen. There's the digital lines, the horizontal and vertical sync come over there. No changes there. I've got enough code done that I can see it works. This is a text mode demo app where I attempt to scroll it using a font that I just made up while I was typing in the bits for it, and it includes, hey, underline mode. That's cool, right? I guess, maybe.
So here's my Raspberry Pi that I use for development and burning the flash image over to the Nouveau board. And I've been doing various test implementations. This is the original one that just simply runs CP/M on the serial port. And then I played around with different types of I/O interfaces with bus synchronizers so that we can make sure that when we communicate with our VDP, we can do it better than TI did with theirs, so that we don't end up with metastability issues when it comes to doing things like reading the interrupt status bits. So I think I used this version of the Nouveau to walk through some test bench ideas that I had in the last video that I recorded. But this one right here is the one that I'm going to focus on today, along with the library files in this directory here and down here. I'm focusing on implementing the TI99 VDP. We've all seen this manual on my channel before because I used this chip on the Z80 Retro and learned about some of its shortcomings. So let's look and see how I did this. So far, what I've implemented was all these control registers and these graphics mode 1, graphics mode 2, and text mode. I'm not going to bother with multicolor mode. I don't know whoever uses it anyway. And even this manual says that some of the TI chips don't even support it, so why bother? If you're hung up on it and need it for some game or something, let me know. Maybe we can take a look at it. But unless, there's really a reason to do it, I'm not going to bother. The other thing that's missing in this current piece of code are sprites. I've got everything, as far as I know, other than sprites working correctly. So let's look and see at the overview of how all this fits together, because if you're trying to follow along, at least for me anyway, I can never figure out what's where and all this other stuff. So rather than diving into the minutia today, I'm only going to look at the top level. Maybe we'll look a little bit about the register configurations and the synchronizers and stuff like that, because I did many different ideas and how that works, and maybe that's as far as we'll get today. And then at another time we'll look at more into detail at the various modules in the VDP itself. As you can see, there's a whole bunch of modules down here, including the interrupter and so on, and the overall finite state machine that runs the whole thing. Each of these is filled with all kinds of interesting details and nitty-gritty pitfalls that you can fall into if you don't realize kind of where you're heading ahead of time. So that's kind of the purpose of today. So let's start in here and look at how the build actually works. This is very similar to how I've always been doing it, but I did add these includes here. So what else have we got going on here? So what I've got is I bring in various files, the make rules. I explained this on my channel ages ago. If you're not following along, let me know, send a comment below or something like that. I can maybe dig up the old video for you and add a link or something, or maybe someone else can post it. that might be useful. Anyway, the VDP99 and the utility libraries are both identical in structure, so I bring them in by first defining where they are relative to where I am when I compile this file. So they're in up one directory and then in VDP99 and lib, which you just saw a minute ago before I CD'd into the directory we're in now, which is that one there, okay? So what do I do with these? I go in here. Not that one. This is something that we were playing around with when I had a bug. It's commented out, so it doesn't mean anything now. I include these two files. And this is something that we need to make sure we all understand so we don't get disoriented. This was the easiest way that I could come up with how to do this. After using, the ISE, the Xilinx ISE for their Spartan chips and stuff in the past, I was never happy with what happened when you have all these separate modules and stuff like that. How do you go find them? How do you add them to the project? How does it know which ones to compile, which ones not to compile? It's big. To me, it's a pain in the butt, because if you're going to create like a C program or something, you can just create a lib something or other .a and say, find your stuff in there, please, and ignore whatever you don't need. It works beautifully. But I've yet to see this in FPGA environments. Maybe they exist now. I haven't really played around with the newer ones in over a decade. So maybe they've added a better way to do it. But as far as I know, they're still operating in the let's just create a giant mess and hope to God nobody ever moves a file or the whole build will fail kind of mode. I don't want to do that. So we'll look at see what these includes are doing, and we'll see how it manifests itself right now in the make file, as well as when the compiler runs and the simulator. So you'll see kind of what happens when you bring in these library files. And just so you don't get disoriented, right? So here's what I have now. Remember, I'm in this VDP99 directory. This is where my top level file is. And I usually create a file called top to put the top level in there so that I remember where the top level is. And normally, and I'm going to have to say this more than once, look, I apologize. Some of this stuff really needs to be refactored. Where I am at right now is I did a marathon last weekend to get everything I could in the VDP done. And I didn't get sprites done, like I said earlier. And as a result, some of these probably could use a little bit of refactoring. And I don't want to dive into that until I finish the sprites. Because if I've made a mistake and I got to back up and redo something in order to get the sprites to work right, I don't want to have to do all the refactoring now and then do that. So I'm going to leave it a little messy. And maybe we can talk about in the next video or two, when I do the sprites, the kind of things I might have wished I did, or how the refactoring really needs to work, because I find it very convenient to just throw it all in there and then get it to work and then take a step back and look at what I've got and decide how it should have been organized from the get-go. Yes, in other words, I'm saying I don't bother to design this thing first. I just dive in and figure it out. And that's how I operate in a hobby mode. Professionally, I might do a little more design, maybe, sort of. If you know me, don't post below. So yes, this is I'm still learning a lot myself, so this is going to require some evolution, all right? In the top.v file, which we've seen on my channel before, is not very different than it has been before. The only real difference is that down in here, I've added this and this color palette module down here as a replacement of this stuff down here, which I just simply reached over to the VGA time sync generator thing and just made color bars out of the column numbers. Okay. This, I think, is factored pretty reasonably well. What's not so good, I don't mind mixing a couple of assignment statements with module instantiations. That should be all you do in your top file, or any file that has an instantiation in it should have nothing other than instantiations, or in my opinion, these assigns, because a lot of times you have to create wires in order to connect things together, and you use assigns and stuff like that. So this sort of thing I expect to see in a top.v. What I do not expect to see in my final version is stuff like this. You're not really supposed to mix instantiations with things like these always blocks, the processes, they're called officially in Verilog. And the reason they recommend not mixing the two is because it's very difficult to create a test bench to test something like this, because I now have to test the entire design because this is in top.v. All right? So I'm breaking the rules here just because I'm kind of sloppy. It's been this way for a while. Luckily, they're very simple. Don't put a giant finite state machine in the middle of this thing and guilty. You'll see one of those as we go too. But, you know, this all should officially be factored out. It really should be. And the biggest problem I have with top.v is that I instantiate the PLL in here. Where do I do that? I just saw it a minute ago. Where is it? PLL me. Where did it go? It's so subtle, it's hiding. Even the memory could be a problem. I'm using an inferred RAM in this memory module. We talked about that before. I added something to it. We'll look at that as well today. Here it is. If you instantiate a PLL in here, what you're doing is this module, remember, has a hard macro in it. It has a, come on, out here. First of all, this file is created by the make file. Let's recompile it and look what's in there. If you're not, if you're joining already in progress, this video series. If I make this PLL, right, and then we have a look, see at what's inside there. This thing is using a a library object that's not real. Verilog doesn't know what that thing is. What this does is it goes into the library that comes with Yosis, looks for some module called this thing, and what it does is it's really creating a giant bitmap out of this that simply puts those bits into the configuration binary bit stream for the FPGA. That's all it does. So a simulator doesn't know how to simulate this, is what I'm getting at. And that's a problem. So I admit this needs some refactoring. And that's what I mean when I say I should refactor this. I should refactor that. Because I'm mixing things and makes it difficult to test. All right? And you generally don't want to do that. So, all right. So top.v, since the last time we saw this, project already in progress, I've removed some crud. I threw in some test, what am I doing in here? Yada, yada, yada. This is stubbed in. I should just do this, for crying out loud. And assign the joystick to some pins on the header so I can actually hook a joystick up now, because it's to the point now where I can run Tetris. And doing it on a keyboard and looking over my shoulder at the other monitor it's affecting my performance. So maybe I'll throw this one in a upcoming video. Anyway, so the big leap here is this color palette and this Z80 VDP99 module there. What do I do? IOREC, read VDP, write VDP. This is the same style and mode that dealt with the other I/O ports I talked about before. I define a couple of wires so that I can take the outputs that come out of this VDP99 module and connect them up to the color palette. And the output of the color palette goes to these variables. Those must be wires up here as well. VDP out color. Where's the red, green, and blue? Those should be wires. Oh, they might go directly to the, those are the module ports. They go right out of the module. These are also different. Good thing I looked at them. These are different than they were last time because these are 2 bits. Remember, I just said I upgraded from a 3-bit DAC to a 6-bit DAC. I doubled the quality of my video fidelity overnight. I moved the PCF file up here so it could be shared across all the projects. I don't know if I mentioned that on the video yet. This pin map PCF file is the same one that's used in every one of these builds. I also factored out, as you can see, there's no longer the read and write finite state machines for the pulse synchronizers in here anymore. That's what wandered up and over to this library subdirectory. Okay? And then I went through the existing code and made all of them include the modules from the library, so we have only one copy, not 10, you know, the usual stupid thing that we all do when we start a project, copying things around, and then you got to fix one, and then you got to, I don't want to get into that, okay? Anyway, that's the big win of factoring out the library code. Okay, so what do we got here? You saw that top.v created a memory, it created the color palette, and it created the VDP99 here. And you can see I have a test bench for the VDP99 all the way up at this very high level. We'll see this in a little bit. This creates a control sequence that will program all the registers in the VDP and let it clock itself through an entire video frame, font and all, and so we can look at every single signal from the CPU all the way down to the finite state machine that's running the VDP internally, which is how I debugged most of what's happening. This is the memory image, by the way, that goes in the simulated video RAM during the run. This is the test bench down here. Okay, so very exciting. This is a huge leap. This is super cool. So let's start with this memory thing, because remember that what I used to have in memory was just the image of the boot ROM, which took this file and just said, hey, make a BRAM, a couple of K big, and stick this binary in there so that the CPU can boot from it. But today, it works a little bit differently. What I have now is the VRAM size is now configurable. The reason I did this is because we know that the binary image for the ROM, this is the hex version, which is more than twice the size of the raw binary, right? Because it's got 2 hex digits and a space, so this would be on the order of 3 times the size. It's only about 2.5K. And I've been allocating 4K to that boot ROM image. I wanted to shrink it down because the VDP optimally should have 16K in it, and 16K is all the memory we have on our whole FPGA. So I cannot conveniently instantiate my whole VDP with 16K of video RAM because some of it is used up here for the boot ROM. Let's take a look at how that works in here. That's the change that you saw already on this thing. So what I do is I say, look, give it 3 512K blocks. Now, I chose to express it this way because I happen to know that the BRAMs inside of my ICE40 FPGA are each 512K in size. So I said 3, I meant 5. There's 5 of those. What I want to do is minimize the waste. So I happen to know integrally, this is what you want. This is 2.5K. This is just enough to deal with the ROM hex image when it loads in. Otherwise, this thing works the same way, okay? Now, what I do here, carving it out of the total 16K, what's left, I tell the VDP down here, what else is left? So there's 12K, plus 3, well, all right, this is, the way I look at it, this is simple, but it's not so obvious. What happens is, this used to have 12K in it when I first started tinkering, because the boot ROM had 4K, and 12 plus 4 is 16. So I carved out of the 8 BRAMs above, down to 5, so the other 3 in my mind need to be added to this size. So now we're up to what, 14.5K out of the 16K that we would like to have totally in here. And this is enough for now. Down the road, I will use one of a couple of different techniques we've been talking about on the Discord. If you want to join the fun, see the link below this video on YouTube. We've been talking about doing things like reading the unused portion of the boot flash for the FPGA, and then building a DMA circuit to write it into the RAM of the CPU RAM, and let the CPU boot out of there, not using any of the BRAMs. Or we can leave the boot image in the block RAM, the BRAM. And when the CPU is done booting, when we normally, up here, there's the logic that shuts off the block RAM when we do the read to the magical mystery address or whatever it is, somewhere in here, there's the FE tick thing. This is when we shut off the boot ROM. I talked at great length about that during the retro and the early implementation of this code. What we could do in here is when we turn off the boot ROM, we can take that block RAM and start using it for video RAM and basically double purpose the thing. Of course, if you do that, you have to figure out how to get the boot ROM image back into that block RAM if you're ever going to try and reset the CPU. So there's going to be something going on in there. We'll talk about that some other time. But for now, I wanted to make this configurable so we can play around with these sizes and get as much RAM as we can into the video RAM. Whatever video RAM is excess that doesn't have data in it, I don't remember what I do. We'll see that as we go. I honestly think, in my mind, my goal was to just simply return what's in the least significant portion of the VDP register 7 down here. This is the VDP manual I just slid in. This down here is like the foreground and background color for the text mode and the border and all that. So it makes sense, depending on what you put where in your video RAM. If you put your color stuff at the end in the highest memory and it goes down there and reads it, at least it will find the text mode foreground and background rather than garbage, which would either be white or black or something for the color, if indeed you use the video RAM for that purpose. Anyway, so that's where this is going, and that, if you can't figure that out, that's what that's all about, okay? Okay, so we got the VDP99. We look at the memory. We have, we'll see the memory going on in there. The palette. Now, the way this is working now is I just have had, up until just the other day, 3 bits coming out of the VDP logic to drive the color. What am I looking for in here? The way the color, oh, there's a table up here. Man, where is it? There. Oh, is that it? Yes. So what happens is I had the least significant 3 bits out of the 4-bit color codes hooked up to my VGA monitor, and I didn't care what color I saw. I just saw some color, and I could see that all the timing and the characters and the tiles and all that were working. But in order to get the colors that match the VDP, at least somewhat close, and after all, this thing outputted composite video, which stands for, which is defined by NTSC, which people jokingly refer to, as I've said before, meaning never the same color, because it's just, wow, it's impressive that it works at all when it's in color, but it does. And these colors probably vary greatly depending on the age of your screen and the quality of the tubes in the set and everything else. Even the most modern ones might have a little trouble, although I would argue they're much nicer by the time we've got LCD panels and even the Sony Trinitron tubes and stuff in the 90s, vastly superior to what I grew up with in the 70s. Yikes! And why I'm laughing and beating this dead horse is that the simple resistor DAC that I made, I just guessed at the values. My colors are not going to match perfectly. I invite you to throw in the comments below when we get to talking about the DAC and the resistor sizes and stuff like that. You might find a better set of values to use than what I did. And I encourage you to do so because it works good enough. But my dark yellow is a little green, things like that. Anyway, so the point is I've got a 4-bit value and I need to create a 3 analog signal output. And what I've done is I've chosen 2 different resistor sizes for the red, the green, and the blue channels that come out of the FPGA circuit. And they're in a 1-to-2 ratio. So, for example, light green, I turn on both green bits, that's the full-on green and 0 out to the red and the blue channels in order to get my light green, which you saw on the text screen just a minute ago. That was the color I set it to. So we should see a 3 in that configuration if we poke around in that code. The medium green is only one of those 2 bits will be on, which would be on the smaller of the two resistor sizes, meaning that the voltage would be about 2/3 of the maximum voltage that you would see with light green. And then there should be a dark green in here, or there could be. Sometimes, yeah, there's a dark green. So this would be a single 1 bit on, what we consider to be the least significant bit going into the larger resistor size, which would then create a voltage that's about 1/3 of the full voltage coming out for what would be the light green, all right? And that was what I had in mind. And the yellow and the red and the dark and the brights and all this other fun stuff. I just did the numbers in my head based on the RGB color wheel and just said, fine, we'll just either put 1/3, 2/3, or 3/3 of each one of the colors on as needed to mix and match to make these colors, okay? Now, like I said, my colors aren't great, whatever. But I will say they're a lot nicer than the colors that come out of my real VDP. So even if I completely screwed it up, it looks vastly superior. So I'm going to leave it at that, okay? Your mileage may vary. We can talk about the resistor sizes in the Discord as we go and come up with the optimum solution, all right? So that's what's going on with the color palette. Let's have a look-see at the color palette. It's really simple. It's just a switch statement. So this is just a decoder when it builds this out of the Verilog. Now, these are regs, and normally I use all-new wires for my module ports. I'm getting lazy, as I say. Lazy alert. Now, this is perfectly fine to do. Without it, and you make this a wire, what I'd have to do is define 3 regs in here because I'm assigning a value in an always process block, which cannot assign a value to a wire. It can only assign a value to a reg for reasons that I am baffled with, as is everyone else. When they went over to System Verilog, they removed those rules and created a new data type. They should have called it the WTF type for smack in the head of whoever decided that there would be a difference between something you can assign in an assignment block and something that you can assign in an always block, where System Verilog created a new data type that says you can assign to this whenever you want block, kind of a thing. Anyway, that's why these are regs. Because I didn't want to have to assign extra variables. So what do? We take the 4-bit color. I should have marked this as a full case, parallel case, because all 16 cases are in here, and there are no more that could ever possibly appear. And the compiler, I'll bet anything, if you look closely at all the output, will say something about identifying this as a full parallel case, because that's some of the analysis that the compiler does. I'm going to leave it at that. I'll leave it as a task to the viewer to go find that in there and offer proof that I'm either insane and it did not do that, or that it did, and holy cow, there it is. I'm amazed, okay? It'll be one or the other. There are no other options. Okay, so here's what you can see the codes in here: red, green, and blue. They either get a 0 or a 1 or a 2. These are 2-bit values, right, for each one of these colors. So based on my recollection of how the color wheel works, these are the assignments that I've made. Did I test every single one? No, probably not. But I did play Tetris from Production Dave, who posted it into the Discord, and it works fine, and it looks right to me. So therefore, by gross extrapolation, it must be perfect. Okay, so you saw inside top, it instantiates one of these. And we will see that this then internally instantiates the VDP99 and all these other fun things. Here's the VDP99 itself. And here's some connective tissue and a mixed bag of always blocks and instantiations. More refactoring that I should do. Some other connectivity. Yes. And here's some synchronization logic that I have not yet discussed. We've gone over some other techniques. And I finally kind of threw up my hands and said, let's just do this because it's simple, simpler than the pulse stretchers and all this other fun stuff I was playing around with. And I probably should do this the justice it deserves. I'll put this in another video. Today we'll just look at the bird's eye view of everything. But if you want to read ahead, look closely at what's going on in here and convince yourself that the sync length 2 versus sync length 3 here is as advertised. But as I read it now, like I said, this has been evolving and coming along. I'm not sure that we care about this. Well, I will do a fine-tooth comb on this in another video, and I'll explain my hesitation at this comment right here, because of the way that I know this changed a lot while I was trying to decide how I wanted to do it. And there's reasoning here, and I think this is a stale comment. And off the top of my head, I don't know why I don't just use this now. But I'm going to leave this for another time, okay? There's subtleties in there, and you want to make sure you know it, because what's happening is this is the jump from the phi clock domain in the CPU to the pixel clock domain, which is the 25 megahertz VGA pixel clock domain, okay? And I did a couple of different variations in here. And we might want to have some opinions. I even changed which edge this works on versus another one. So it may be that these are getting a little stale, and maybe we could do better, is what I'm getting at. So I'll reason this thing out in another time. So I'll put that under the rug for now and close with the observation that it works. It's very reliable. I don't seem to have any trouble with it. But like I said, as I look at it, is the case with all software and all hardware. When you look at it, you go, yeah, maybe I can tweak this, So that's what I'm doing in my head right now, and I should never do that while talking, but oops. So moving on, here's the manifestation of the video RAM size parameter. The default is 8K, which is what I've been using until most recently, when I wanted to up it to that 14.5K so that, Tetris can work, and so on. What else do we got? The usual stuff. Here's the CPU clock and the VGA clock. Down here, when you get to the actual VDP99, you'll notice the CPU clock is gone. From here down, we are entirely in the video clock domain, okay? So this is the only time when we do this transition between the CPU clock domain and the pixel clock domain. All right? And I use these to do that. So I'll leave that as a test to the viewer. Now that you can kind of see what's going on, right? So there's a Z80 VDP99 interface. The purpose of this is to connect the CPU clock domain to the VDP clock domain. That's the purpose of this. And if it's not said so up here, and it's not, I should probably add a comment to that effect. All right, I shall push that up. Okay, now let's run this test bench, because when we do this, what it's going to do is, as you've seen before, it says, oh, here's the test bench that I've run, and then it gives you this little set of choices. You can open up this tree menu, and that menu is critical that you want to have a look-see at here. And it'll show you all the modules and where they come from and stuff like that. Now, when I did these test benches, because in the libraries in particular, there's multiple test benches in one directory. And I can also see I'm inconsistent in this manner, so I apologize in advance. A little more cleanup that I can do. I make these test benches in some way or another the targets of these rules in the makefile. And I'm hesitating again, because I know sometimes what I did is I used the name of the thing that's being tested, the unit under test, and other times I use the name of the test bench itself as my make target. I will go through and modify the makefile like this. Before I post this video, I will update. So basically, the idea being, if I want to test VDP99, let's just make VDP99 like this, and I'll make them all the same way. I'm going to put this in the background because, as you'll see, it's going to take a little while to run. And it'll gripe a little bit because the rom.hex file does not have exactly the right number of bytes to fill in the 2.5K. And the VDP RAM initialization file I showed a minute ago for this particular test bench is also not enough to fill in exactly the whatever it was, 14.5K or so, that it needs. So this takes a little while. And you can imagine that it might, because it's simulating every pixel of an entire video frame, okay, including all the configuration, register programming, and the vertical sync, and it even does the interrupt and the status read on the VDP to clear the interrupt. That's a lot of data. All right, so this is a big file, and it does take a little while to load. Now, this is my entire screen for the video capture, and you'll see if I put every signal in there, it'll be like 10 times higher. On my 4K monitor, this thing consumes a better part of the screen. So we may have to scroll around a little bit when we really want to look at the details here. But the reason I open it right now is not to get into that yet, but here's the test bench, okay? And let's open this up. We can see the unit under test is the VDP99. Rather, I should say that's the Z80 VDP99. This one inside there, it instantiates an instance of the VDP99, which comes out of the VDP99 library. And inside there is a finite state machine, a register interface, the video RAM module, the V, I forgot what the V was. The V counter video. Oh, this is the VGA synchronization signal generator. I probably should name that a little more obvious. And this is the VDP interrupt request finite state machine as well. That includes a proper way to read and interrupt status when you're not actually in the interrupt handler, so you don't create this metastable state where you either miss one or read the same one twice, which is what happens on the actual TI chip. If we want to synthesize it sucking, we can do that. You can actually comment a few things out in here, and it will generate garbage interrupts, and it will stink just like the other one does. I prefer not to have it do that, so I did this one. I'm air quoting right now. I'm not on camera, but I did it right, or right-ish. Better, I should say. Okay? Now, why are we looking at this? You'll notice this right CDC, this thing, that thing, and the color palette, and the memory. What are these doing here? And what's up with that? Okay? These exist because of what I was talking about earlier about this idea of how I'm going to do the library files for this project moving forward. What I'm doing is I'm just saying, look, when you compile it, or in this case simulate it, compile everything and throw away what you don't need. I'm very happy that the simulator does not generate errors saying, no one's using this, no one's using this, I don't care, all right? I don't want to have to hack up make files and keep everything perfect, and they'll never be right, you'll forget to put it in here, or there'll be too much or too little. Giant pain in the butt. Just compile everything you can find. And how do we do that? What does that mean? What do I mean when I say that, right? Okay, here's what I mean. In this makefile, what we have here is I define these includes here. I include the data from these make files over here. These make includes in the VDP99 directory, which you define up here, and the library directory, which you find up here. The test bench files exist independently of the regular files, which you can see includes the test bench files. The idea here is these includes over here define respectively these variables. If I include the VDP99 library files, this makefile will define and set a value to this variable that includes the names of all the files in this directory over here, which is this guy there, right? Same thing for all the files in the lib directory tree structure. So I don't have to list them all here. Like I said, in the Xilinx ISE, every time you do one of these, you got to like drag and drop or open and define every individual file every single time, and I find that very annoying. Just go. This is the Captain Picard. Make it so. Get out of my face. So this is how I do that. Now, the fact that I have test bench files that are separate than the regular files for the compiler is because of what I told you about this thing and that thing. These guys we cannot simulate, so I had to put them in kind of a separate grouping. So these things are things that can be simulated, and these include all of the above plus what cannot be simulated. So when we compile the thing, which is done here, we list all of the files as dependencies, and it compiles everything. Even if it doesn't use them, they're all in there. And you'll actually see, we'll look at that today as well, the compiler saying, why is this here? And throwing them all away because we don't use certain things anymore. They're in the library, but it's not currently in use. The test benches down here are used like this. When I say, well, if I'm going to run the simulator, which is that, we talked about this before, and I'm going to use this file here as my test bench, these TB files are all the it's funny, nice naming choice, John. These are all the files that the test bench might need, not including the test bench itself. Okay? We certainly do not want to put the test bench file in the real compiler. You cannot compile a test bench file that has delays and all this other junk in it. It might compile it, but it certainly won't do anything sane with it. And they'll probably have all kinds of errors and warnings anyway, because it doesn't make sense for non-simulation code. All right? So that's what's up with this make file. That's how this make file finds the files that are in these other directories like VDP99, because there's a little make file include sitting over there. And if you look what's inside of it, we say, here are all the include files that come from the directory in the VDP99 tree, okay? And again, I use this variable here, which is supposed to be defined before you include this, as a little comment in there, because this guy doesn't know where he is relative to the guy doing the including, okay? I could have used the top variable. I kind of went back and forth on that. I decided to say, look, in order to use this include, first define live VDP99, which is probably that, okay, from wherever it's being included from, and then go ahead and include it. If you do this, then that is defined, and then it can be used in here, whether it's a full path or a relative path with a ... / whatever in it, as is the case for me. And then these are all the files that are in that directory that are relevant if you want to compile this stuff. That's not what I wanted to do. There we go. And you'll see that this does not include all these test bench files and other junk data and things like that, and the README and documentation and stuff like that. Okay, so that's what's going on here, and the same thing's true about the library directory. There's a make include there, and this one's structured a little bit different, so let's go ahead and look see. As you can see, this one has actually subdirectories in it. So the idea with this one, I mean, I could have either put a make include in each subdirectory and have this one do the other one. I don't know. Whatever. For now, I'm happy with this. And these are all the things that are in this library that could be useful. Now, at one time, I did use all of these. And because of what I said with the Z80 VDP99 file, oops, come on. This thing that I was just yammering on about, this big test bench that is the test bench for that thing there, and the fact that this is the clock domain crossing interface module from the CPU to the VDP, this thing used to use all these, but I threw this one out and that one. I don't use them. I talked about this in another video, and this one I think is a variation of this. Anyway, I created a bunch of things, and I may or may not use them. Okay, but I left them in the library because I did test them. They do work. They do what they're supposed to. And that's why when you do something like this, you know, there was a point to all that, you see this junk up here. That's because the simulator was told to compile these, but nobody ever instantiated them. Okay? Now the simulator will actually run what's going on in here as well. I mean, there are time steps. If we look at what's in here, I don't really know what it's going to do. Probably nothing, since it's never actually really, it's not instantiated. So the inputs are not hooked up to anything. So everything is either high impedance or unknown. All right. So you're going to see extra CRUD in there, is my point. All right. You know me, very, very direct and to the point in terse. Yeah. Okay, let's cut this out of here. Okay, so that's what the extra junk is in there, because I just compile everything. It also lets me know when something gets so stale it stops working, because it will try to scan all those files, and it will report, you know, syntax and errors and things like that. so I can know to get rid of them or whatever, or update them as I go. So what are we doing here? Let's go ahead and look at the big picture of the whole ball game. So this is unit under test. This is the Z80 interface. Okay. And if we take all these files and we append them to the chart, that is a whole video screen frame. This signal right there, that's the interrupt request going off. And I very carefully chose when I wanted to generate the interrupt. In this situation, you see these little spikes down here? That's probably the vertical sync. See that right there? I fire my interrupt way before the vertical sync takes place. Because, and if we zoom in on this, we will see that what's happening here, this is the color output. 4 is my border color. Now, unfortunately, it's also the background color when this thing runs, and there's a bunch of tiles on here, but you can see this pattern changing a little bit. What happens is, let's zoom in a little bit right here. What's going on? What's going on? There's a little thingy right there. There's a pixel. There's a 3, 4, 3, 4. And what's happening here, this is a foreground and background color of some pixels that are on the screen. I don't know if these are all 3s and 4s. I don't know if this is in text mode or not. We'll have to, I mean, we'll look at all this in another video, but in order to get our bearings straight and just, you know, kind of understand what's going on, what I did is like I said, I rendered the entire thing of every clock, every pixel. You can see all the horizontal sync pulses in there, and there's the interrupt request. It goes off. My point is, it's rendering the border at the time the interrupt goes off. So it's still actually drawing part of the screen that you can see. This is the bottom border, is what you're looking at. And who cares if I fire it early? It gives the CPU more time to update the video RAM, because the CPU, or the VDP rather, I should say, is not using the video RAM during this part of the screen. So why wait until you're all the way down at the bottom of the screen during the VSync period when you only have this little amount of time down there, relatively speaking to what would happen if you fire the interrupt way over there? You've got, and look at the side. This is the whole pixel. The whole width of the vertical retrace was a couple of rows. This is all the way up here at the bottom of the border. Now, I would not be surprised if VDP does the same thing. We can try to calculate what it does based on the time in its manual, that it says you have this much time when the interrupt goes off to access the memory at full speed, and then you have to slow down the rest of the time. You'll see in my design, we can access it at full speed all the time because the way I did this. And we have faster clock speeds and stuff like that. And with all due respect to the designer of the VDP, the only thing I really don't like about it is the crummy interrupt status bit. That, I mean, obviously it was designed only to be read in an interrupt handler after the interrupt went off. And therefore, you avoid this metastability that we saw happen when I went over it on my channel before, okay? While we're here, let's just zoom in really close at the very end. Now, what happens is this is difficult to do. So quite often, difficult meaning, you know, when you zoom in, this thing is moving around horizontally all the time. So in the test bench, you'll see I generate a whole bunch of clock cycles over here. And you can clearly see that here's the feed clock for the CPU. If you want to poke around here, here's the pixel clock. They're both running at different speeds, and they don't stay in phase very well, and they slide around. This is your clock domain crossing, okay? And what's happening here is the interrupt is high. You'll notice it goes low right there. The horizontal sync goes high, it goes low. In my test bench, I wait until over here to read the status register. And if you go look around, the status register is in port 80 in my design. No, that's the value. That's the bit. There's the frame flag bit that's on. Somewhere in here, there's the CPU address mode. Oh, at this point, what happens is we're not looking at the whole address bus from the CPU because we're down here. And if you look at the test bench, what happens is, or even in top.v, we don't pass the whole address bus into the module. Who cares? We decode it up at the top level. It gets one bit. the least significant address bit, which the VDP calls its mode. So it has only two addresses, port 80 and 81, and it kind of confused me because the value is also 80. If we reach up into the test bench, we can see right here the full address bus and throw it on here as well. And if we zoom in on it, you can see that what we're doing is we're executing a CPU read operation from port 81, which has this 80 in it, which is the value of the status register when the frame bit is on. You can also see the synchronization logic working down here if you want to go and play around in the interface module, which is this unit under test that we were just messing around with there. And you can see here's the state machine. This is a shift register that it uses to do the synchronization. To do this, you'll see these edges line up with the pixel clock in order to interact with the VDP in its own clock domain, independent of the CPU clock domain. Get the value during this time here, save it, and then send it back to the CPU in order to see that correct. Well, that's what this data out value is for on this screen here. The data out is obviously the name of the port that's in the interface, the Z80 VDP interface module, and you can see that in here, right? So this is how we navigate around, and this is, I spent a lot of time looking at this thing, debugging this code when I was going with it. Let's look here at the very beginning as well. You can see a lot of chatter over here. If you look and zoom in on here, what you're doing here is you're seeing all, these are the 7 VDP registers and the values getting programmed in here. Something's got a program of a 0 there, and another one is over here. This is probably register 0, getting set to a value of 0, because you remember from the documentation what happens in here. Again, get the bird's eye view before I just dive into the details next time. When you program these registers, it's the next section here. How to write to the VDP registers. You first send a data byte, then you tell it what register to store it into with this top bit set to 1. All right? So if you look in here and you watch what's going on, you'll see the CPU sending 2 byte values in order to program one register. And what they're all written to port 81, which is why you see the address 81. It's an odd number. Therefore, the least significant bit, which is the mode bit for the VDP, is always 1 when it's transferring the data. This is, I can see the worst case timing just to make sure everything's fine. And it actually did find a little, it helped me figure out how to do the synchronization logic down here, because I had to kind of cheat a little bit. And I grabbed a value here on this falling edge. I don't know if that was this data in or the address or one of the values, in order to get it a little bit earlier. You saw in one of those comments in there about whether or not the I'm going to use this part of the shift register to determine whether I'm going to read it from, or this third one over here, or which one it's going to do. Actually, I think it's still set to the third of 1. It starts with 0, which is 0 all along. Then it goes to 1. Then it goes to 3 in terms of the shifting these bits through here. I'm looking at it upside down. Sorry about that. The 1 double 000 100 110 is the little time window, I'm saying, when I decide to assert this tick signal here to say at the end of this period is when I want you to capture the data. And this thing can wander out of this timing here, which is why, and we'll talk about it in more detail later, you can look at it if you want to get ahead, is why I latch this data in value, which is probably this thing right here, okay, and stretch that out. This is a different kind of stretching than I did before. It's kind of a mixed bag of these things in order to make sure that when the data is present, or the port, that I hold on to it long enough to be able to store it in the VDP register. And if we look closely at the test bench, what happens is there should be a T1 synchronization signal in there somewhere. Tick, sync, read, tick, write, sync. Actually, I'll bet it's way up here. Is there a T1 marker? I did this before. when we're playing around with making sure things work with the synchronizers. These are time pulse number 1 in the Z80 documentation. And I think we've seen this manual a couple of times, or one of the manuals that has all this fun stuff in it. And here somewhere, there's a timing diagram, and it tells you, yes, there's the read and write cycle in different modes. Here is the thing where it fetches an instruction and does some, what is this? The full, that's the, okay. This is an interrupt acknowledge cycle. There it is. There's the one that we looked at, I think. Before I do the wrong one, yes, the opcode fetch and IO timing diagram that we lovingly spent going over. See this 1, 2, wait, 3 for the IO cycle here. The opcode fetch cycle is a 1, 2, and a 3. They show the wait, but they also show you requesting a wait. If you don't request a wait, and I do not, this is a 1, 2, 3, then a 1, 2, 3, 4, because, 1, 2, wait, 3. There's 4 of these and 3 of those in the mode that we're running, which is why if you zoom in here, you see a 1 with a 3 phi clocks right here, another one with 3 phi clocks right there, and then here's a 4 phi clock jobby that's doing the IO operation there, okay? So this lets you see what's happening when the simulated CPU is writing to each of the 8 configuration registers and the values that it's putting in there, okay? So I believe the last one is going to be register number 7, which you can see there. The 87 is the high bit set in the manual you're just looking at, followed by the register number 7. And what I do is I put a 34 in there. 3 is a green background color, and 4 is, I don't know what, maybe that's a blue or something. Where's the colors? Where's the colors? We had them on here a minute ago. 4, a dark blue. So I must have a dark blue border and a light green font when it's in this mode that's being simulated. What I showed on the screen is actually a 31, and I actually remember hacking the test case code because I wanted my border to be black. So that's probably what happened there. I got a light green on black that I showed you on the video in the test program. Okay, fine, I'm jumping all over the place. We can also see, if you go over to the Z80 Retro example file system, there'll be links to all these repos on GitHub below. On YouTube, you can see, let me clean this up, there's a lot of files in there. This text.asm is what I'm thinking of off the top of my head. I tried to use all the same values in here, and that is the value for the foreground, background colors in this test program that I wrote and assembled and run on the Nouveau CPU, and sends in all this data here. You can recognize these things from what you saw at the beginning of this video, and it's green on black, a lot like what you're seeing on my desktop here that I'm recording. Okay, so at one time all these matched, and then I decided to make them different just to confuse myself and everyone else, all in the interest of beauty. Okay, so in the test bench, I do a bunch of register operations, and then I let the clock free run, and I watch what happens with the entire video frame, and then I have some test bench code way at the end that plays games with the interrupts, which I can't seem to zoom in on. Yeah, if you work on it, trust me, they're over there. They're hiding in the last pixel off to the right, okay? So that's the top level view of all of what's happening. Make clean, get all the noise out of the way. What's happening in this build, where the files come from, and all that fun stuff. Real quick look at this text bench in here. And the last time I recorded a video, I was driving myself utterly insane creating this test bench. That's when I said, hey, wait, let's use these techniques that I've known about. I've seen them in books, but not in the context that I decided to use it. It didn't click until I was doing this, and I decided I was building things based on a waveform diagram, and it was much easier to do this. And I talked about that at great length last time. Somebody then in the Discord, and that's the point, that's why we're looking at this right now, said, hey, if you do this, it's kind of like having a subroutine call. And I said, that's a good idea. There's actually a more official style of doing this. If feel free to let us know all about it in the comments below. It's called an event trigger, which I have yet to talk about in my video series because I have not used them. I'm no expert in them. I'm not really an expert at anything. I can make things go, and that's what I'm really talking about here on my YouTube channel. I know enough to get by. So this is the I know enough to get by way of doing this. I've read some articles and some doc on how to use these event triggers, but when I look at them, it doesn't set in well with me, and I have enough going on in my head. I really want to get the VDP going, so I went with what I know versus what I need to learn, okay? And I'm not going to talk about it and present anything that I learned less than an hour ago on my YouTube channel. So if you are an expert with these event triggers, let us know, and maybe we can tweak this and decide to make it work. Meanwhile, this is very similar to my understanding of those things, and it solves one of the problems that a lot of people gripe about. If you Google, how do I use Verilog event triggers, the problem is you can lose the event trigger and miss it and then stall. Because if you're not waiting for something, by the time it does happen, you will not get it. And the same thing is true about edges. Those event triggers that you get in Verilog are really, in my opinion, they exist, these ephemeral points in time. Just like saying on a positive edge, do something. Well, if you do something in simulation, and whatever you do takes multiple clock ticks to complete, if another positive edge occurs while you're doing something, and that's exactly what's happening here, by the way, because when this thing runs, look at all these pos edges in this sequence of code here. This takes time, and a simulated time to complete before it gets back up to the top of this loop when it starts waiting again here. And we'll talk about that today, and then I'll wrap this up. The problem is, if you don't get back up here, if this was waiting on an event, a point in time, or an edge, and you'll notice the way I've written this, it does not. So I don't have to worry about the problem that everybody complains about with regard to event triggers. This is waiting for a signal level to become a 1. And if it has already become a 1 before this wraps around in this loop and gets up to the top here, it's fine, because this condition will be false, it falls down, and it keeps going. This won't stall. If it goes around here and gets here late, look what I'm doing. Well, this is not a 1. Wait for a clock pos edge to occur, I'll come back up. Is it 1? Nope, wait. Was it 1? Nope, 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 wait. Oh! It's a 1, fall through here and do this. This is what I went through the other time in the previous video on my YouTube channel, doing wait, go, raise the data and all that other stuff, using the time values and the offsets and the delays from the waveform diagram that you just saw a minute ago, okay? And what's in this loop is two writes to those registers. You can see a simulated opcode fetch, operand fetch if you're running an out instruction. And then down here it does the IO write cycle, and you can see it uses this thing here called VDP register value. This is a variable that exists and is documented up here for the sole purpose of being the value that this loop will write out into the VDP register, whose number is right here, by doing all these things in this series of time, so I don't have to replicate this code 8 times in my test bench. So what happens is you write a 1 bit into here, this loop runs top to bottom complete, and then it comes back up here, and if it's still 1, it'll do it again and again and again. And we'll notice at the bottom of this loop, right here, it writes that register to a 0, put a 0 in it. This is the handshaking. So if it does this before it comes out the bottom and goes back around to the top, it'll do it once and stop. Okay, now we're in simulation, okay? So we can write a value into this register variable from more than one process, which is another thing you cannot do when you're synthesizing code. It's not really well advised anyway, but this works out very nice for this, okay? It's good enough to get done. Notice I say the reg, I set a value, I put a 1 in here, And then I say, wait until the thing I just set to 1 falls to a 0. When is that going to happen? It's going to happen when this looper comes all the way around and says, okay, there's a 0 in there now. Now, why did I not wait until down here? I did this on purpose because I wanted it to acknowledge that it's done before it's done, so that this thing can wake up and get the next one in line as soon as possible. This can't overrun, because what it's going to do is it'll set this write reg back to a 1 again, and it will do it early. Okay, if you were doing this with event triggers, this will not work. It would deadlock, because you need to wake up the other guy, the producer, the event consumer is the code you're looking at here. This thing would have to be way down here, or at least in terms of time. It'll have to be after the point in time where we know this will complete, get back up here and wait on what would be an event trigger before the originator that's going to post that event does so. But this one, the guy that posts that changed this to a 1 can do it before we come up here. And this is a big deal, okay? But this is why this works. And this same style needs to be adjusted a little bit if you're going to use triggers. I did it this way, and I did it early, specifically so that when you look at the waveform diagram that comes out of the test bench, that based on what I know in this technique, the time that it fetches the following opcode happens on the exactly correct phi clock pulse that immediately follows the I/O operations T3 pulse. And if we come back in here and look again in here, remember these are the T1 markers right here. There's the I/O operation. So when these are back to back, my point is that this rising edge here, I want it to happen after the T3, right? So here's the rising edge that represents T1 of the I/O operation. Let's throw down this white marker there for where T1 is. So that's this phi clock there. Here's T2. Here's T wait. Here's T3, and in order for T1 to come right here, as you can see it's right there, right away, the test bench that gets ready to set the next register up has to start, before the loop that's doing the register write logic that we're just looking at gets back up to the top. And that's critical, because you see what's happening down here. And again, we'll look at this more closely another time if you're going to work ahead. What happens is this sync guy here, what I was concerned with, I want to know that this thing gets all the way over here and is ready to go again before it needs to start going again. All right? If you wait an arbitrarily long time, in other words, between this instruction, which is being simulated from here to here, that's one whole out instruction. Opcode, operand, the port number comes into the CPU there, I/O operation here, and then we start a new T1 to do another output opcode, operand, and then the I/O operation here. Well, the VDP doesn't give a crap what's going on as long as we do not take forever in here to reset all of our stuff to get ready for the next operation that writes into a VDP register. So as designed, this VDP will not work, because what has to happen is this has to go back to 0 for one full pixel clock period. I'm having a hard time zooming here. There we go. Hello. Oh, I have the wrong shift key down. Okay, there we go. So technically it's hard to see because the 0 starts early, right? But it starts with a 0. Then you get the 100, and this is in binary. So I got a 110, 111, 011, 001. This 000 here has to finish. Actually, this is in the phi clock domain, but it just so happens these edges are pretty close. They are pretty much never right on. And this is huge. This is where your metastability can happen if you don't use the right clock domain. So if we look very closely at when these change, they're on the rising edge of the pixel clock, which is this guy right there, okay? So what I'm getting at is if we assert what will be this VDP mode tick signal. This is when this clock domain crossing logic says, okay, I'll now transfer the data into the register. This can only happen when I got a 110 in here. And I can't get a 110 unless I start at 000. So it's critically important that the next sequence of events where this write synchronizer, which is getting its input from the I/O, like write signal up here, or like the VDP write tick or whatever it's called in the various different modules, okay? This thing has to happen while this is 0 before the rising edge of this pixel clock, okay? In order for it to move on to a 1 and so on. So if that doesn't happen, you know, in other words, if the next I/O operation starts here, this won't work right, and it's too soon, and it will not consume the data. You must wait until over here. That's why I went to great agony and mental struggling to decide how I was going to do my touch bench with this little spin loopy thing in there. All right. So I wanted to make real sure that I didn't miss what was going on when it comes to, this thing. I want to make sure it spins around as fast as possible in the worst case timing, all right? Which is what I now have because I let the below code start running early enough for this thing to continuously spin and never wait when it's rapid firing out all these value and register number, register number, and so on. You can see some comments in here. Sometimes I want to simulate graphics mode 1. Sometimes I want to go graphics mode 2. It's currently in text mode. That explains why I have the green pixels and the whatever the other one was, the blue one. And I comment these in and out based on what I want to simulate. So right now it's set to text mode. If you put it in graphics mode 1 or graphics mode 2 or whatever, we got interrupt enabled on, interrupt enable off, all the different modes, okay? So I encourage you to look around and play around with this if you're really into this sort of thing. Plus, if you're in mode 2, you have a different value for there. So yeah, I'm using this to debug all kinds of stuff. I used to have it ending early, the usual stuff. You tinker around, make sure everything's what you want so you can zoom way in. So what am I doing? I'm writing in the 7, or the 8 rather, 0 through 7, VDP registers, and then I wait until the VSync signal ends. So this is an enormous number of clock ticks. Oh, that's why this was in here. Early on, before I had this thing working, I never got a VSync signal, so the simulation would never end, and I had all kinds of problems. So I just said, here, go a million ticks or whatever, and so I can watch what's happening and why the thing didn't work. So I left that in there for handiness. So where's VSync? Oh, that's this little pulse way down here, right? That's right, VSync right there. So what it's doing, all right, if you want to play around with this, it's waiting for this falling edge right there in the simulation. So it writes out this entire frame, interrupt and all. The interrupt will not be asserted if you use, obviously, this config, a 70 or a 50 going into register 1 instead of the 70, which turns on interrupts. Okay, so that was what I was using to test that at one point, obviously. So we wait until the VSync ends, then we dabble around because I know based on the mode that I've set, I want to be able to read the status register, and I just do that in a simple set of, these are roughly the timing for a T1, T2, T-wait, T3, kind of a part of an I/O operation, just to see it go and make sure that the interrupt does in fact reset. And I think I was actually playing around with some other timings where, like the interrupt request signal itself, where is it, would be read at a weird time so that the phi clock doesn't really line up. You can move this thing around a little bit in how you do your test bench to make sure that if you read it while it's changing its value, by definition, it will change its value during the read. In fact, it does. You can see that right here because reading it, this is the read operation. The IO request is taking place, and you see the VDP yanking this IRQ out from under its feet in the middle of this read instruction cycle. So it's critically important that when you get this value and you return it, which is in this 80 right here, that you return it and you extend the value beyond the value that it is in the register, because the register is going to reset it when it does this. And well, like I said, we'll walk through the interrupt requester logic later. But again, this is one of the things that I needed to see, and this is what this test bench is all about. And what I do is I set the data output from the VDP module to the value from register 7, and I keep it there forever until the CPU wants something else to make sure it's there past the hold time on the real deal read operation in the IO rec and all that other fun stuff. Okay, so this is, again, this is one of the most useful test benches that I remember pretty much that I've ever written for any project that I've worked on. This is pretty cool. It does like all these little simple things, but we get a lot of value out of it, and that's what this giant loop is for up here. You can thank the Dino Wiggle the mouse in the Discord for that idea. Thank you very much. It's a time saver, a typer, a fingertip saver, if nothing else. All right, so there's the bird's eye view. Hopefully this doesn't go too long. At the next time we go through this, what we're going to do is we're going to take a closer look at each one of the thingies that are in the, the various VDP library. How does it, this has been revised to add more stuff to deal with borders and stuff like that on the TI99, which I didn't have in there before. And, what is it? The register interface. There's the interrupter. There's the finite state machine, which I will admit now needs some refactoring. Here's how we talk to the video RAM, and that probably needs some refactoring as well. The video RAM module there implements the its own state machine is my point. I've decided to go ahead and do it that way because it was easier at the time. And what that does is it implements this 3-byte whammy. You got to send the 2 address halves followed by the data in order to write a value into the VRAM. And you do a similar thing to read it back out, but the timing is different because the data arrives. Anyway, so all that's buried in the video RAM, okay? And for the most part, we've already seen the things that I moved over here. They're in the IO rec subdirectory of lib. If you want to find those, oops, I typed it in wrong. Library IO rec. And you can see the read and write finite state machines and their test benches over here. These are just, I just moved them over rather than keeping 80 copies around, okay? And these here I talked about before, like I said more than once in this video. Right now, those are not included in the implementation, even though they appear here, which is why you'll see the compiler when it runs say things like, I'm removing this unused module, which I can go here right now and give you a quick view. Here's what I'm talking about. Oops, that's not going to be found. There is usually that warning about the tri-state, which we've seen before. And you see it now. Actually, let's go to the very top, because this is like right away. Comes in here and it starts scanning the top module, and it says, oh, remember, this might not work. But it works fine because we did it the one way that Yoast knows how to do it. And then it says, okay, I'm reading the memory V, I'm reading VDP99, the IO request. It's reading all these files because I told them to use those from those include lib and include VDP thingies, and they all come in here. Now look what happens. It gets to the bottom of all the stuff I told it to do. It says, okay, fine. Now, I'm going to go over to these directories because when they install Yoast, it says, where do my libraries go? Well, they go into like user, share, whatever. And what happens is these are all the things you could put in your code if you wanted to create these hard macros. All right? And we see some of them in here. There's the PLLs, right? If you want to create your own RAM using a hard macro, you can. You can obviously do all various flip-flops and program the LUTs and everything else directly as you want, if you so desire. Here's how you create these global buffers, and we've done the SBIO. And we've seen what those do in projects earlier on my channel as well. Some of these are not in the ICE40, unfortunately, because they have a hard sell for an SPI, and some of the other chips in the I should say they're not in the HX family of chips, but the ICE40 as a whole does have SPI and I2C and some LED drivers and things in some of the other chips, like the what was it, the UP-Duino, the ICE40 UP chip has some of these on it, for example, right? And here's what I'm talking about. So when it runs and it says, hey, here's the design hierarchy of all the files you told me to load, and here's all the ones that got instantiated. And let me rephrase that. Here's all the ones that got instantiated based on what you told me to load. So I actually told it to load in and parse. You saw I'm parsing above more than just this, okay? Like the pulse stretcher and stuff was in the big list of all the files. But these are the ones that I've used, all right? Now what happens is it says, look, these are the parameters that you specified when you created some of these modules. So watch what happens. It goes, okay, you told me to build that. And then you said, well, I don't want you to create a VDP with 8K. I want you to do one with 13K. And the default, so it does one at a time. It comes through here and it says, I'm not going to just take the Z80 VDP99 with the 8K default. I'm going to use the one you told me, which is this. So it does this weird substitution thing in here. And then it says, here's all the rest with the 8K and all this other fun stuff. You'll also see that it also expanded out and revised the VRAM size for the memory module. These are currently wrong. It makes another pass and goes, oh, wait a minute, that propagates down to here. So now I got this and I got that one. And then it says, okay, now what do I do? And it goes over and over and over, and it just keeps expanding this and revising these until it gets the final draft, which is then here. It finally gets done and says, okay, these are the final numbers for all the things that get passed down with these parameters. Then after that, it says, I'm not going to bother with any of this junk because I don't need it. This confused me a lot, which is I'm in overtime here. I'll make sure you understand. It threw away the memory, the VDP, all these things that I know. Well, actually, these two we don't use at all. But I'm like, what do you mean you're throwing away my VDP? I was very confused. Okay. So the way I figured out you must have to read this is when it does these revisions, it replaces the generic VDP99, for example, the Z80 VDP99, I should say, with this one here, with an overridden default size. All right. So that's why it's throwing away all this stuff you're really using, as well as the default sizes of things in here. Okay. So now you know where they all come from. You know how they hook together. You know how to look and find this in the output of the compiler, because if you start playing around with things, you might comment something else out. Or what happens is, I found this very disorienting, but it's a cool, great optimization, that the compiler does. Why does it throw away something like this in your design? I mean, I told it to do this. Why didn't it do it? Well, in this case, there's two reasons. Nobody instantiated either one of these things. But if I use something like the VGA synchronizer, okay, and this outputs the vertical sync, horizontal sync, the row and column counters. We talked about that before, right? Let's say for some reason I create one and I instantiate it and I really want it to be in my design, but for some reason I'm debugging and I comment out something and none of the outputs from that module get used anywhere. If I don't consume the horizontal sync, vertical sync, or whatever, the row counter values, it may decide no one uses what this thing is doing and remove the whole thing from your design. Now, sometimes I want to be able to do that to figure out how many LUTs I'm going to need before I really finish my program. Be careful. If you do that, because it'll tell you, oh, I did the whole thing with 4 LUTs, but in reality, it needs hundreds of them or 1,000. So it's funny. So this is all part of the optimization, okay? Don't do what you don't need to do and remove all these, vestigial things that it doesn't need. And then, the usual stuff as it goes. And this is now doing a fair amount of stuff, which is why if you go through here, you'll see it's doing this, it's doing that, it's optimizing. You'll see a lot of ALU operations because we're adding and we're comparing the size of the counter. When the counter is less than this, which row am I in? Which column am I in? And you'll see it trying to figure out how to, you just saw, the efficiency of this is this versus some other thing. And trying to figure out the best way for you to do this thing. Uh-oh. Verilog, not found. Well, it says interrupt. That's probably because I hit Control-C while I was compiling this thing. If I do a make world and don't hit Control-C, let's hope it still compiles. And it's fine. So yeah, I broke it when I was clowning around with less and stuff like that. Now, one thing that I did remember, I saw go by in here, it tells you how many LUTs we need to use. So what am I up to? I'm almost up to 1,000. And it's interesting because it was not very high at all. It was less than 10%. And this is actually great, by the way. I was originally concerned. I don't know how many LUTs I would really need to create one of these VDPs. Maybe it won't fit in there. Not bad, 12%. But we don't have the sprites done yet. Okay, so that'll use something. But I can't imagine it would need more than 88% of the LUTs in there just to do the sprites. I am surprised it went up to here, by the way. And that's, okay, let me rephrase. I'm shocked that it's less than 1,000 LUTs, number one. Number two, until I finished debugging text mode, this number was on the order of like 400 or 500, which was just flabbergasted me that I could get all that done with just a couple of hundred LUTs. So this actually, the compiler is pretty good in spite of the fact that it's this open source thing that's probably not optimal in a number of ways. So what am I getting at? The difference between text mode and non-text mode is like significant impact. And if you scroll through here, it wasn't until I started doing text mode that it really took a long time to compile, and it was really playing a lot of games and spewing a lot of stuff in here about ALU things and carry chains and all that. And I don't know for a fact, but I believe what happens is this tax to implement text mode, if you think about it, text mode, the number of characters per line, which is down here is a pattern table. How does the pattern table work for text mode? And da, 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 da. Look at the screen dimensions. It's 40 by 24. Neither of these is a power of 2. In graphics mode, this is 32 by 24. In this horizontal column counter, the pixels here, that's going at the full speed of the pixel clock. Everything else runs slower. So the critical time path when it wants to build the fabric that goes inside the FPGA is based on the column counter up here. And one thing that happens once you go into text mode, I have to compare this against a number that is not natural in the binary world. As soon as I did this, the thing started falling apart in terms of how many LUTs it needs. Now, it did figure out how to do it and still run pretty quick. I think the timing number, where did the timing number go? It's in here somewhere. Where's the thing where it says, ooh, I can run it at this fast. There it is. Ooh, we're all the way down to 43 megahertz. And I believe that, I'm sure, okay, I'll put money on that. I'll bet a beer that this is caused by the carry chain and the text mode magnitude comparing logic when it decides that it got to the end of the 40th character, which is really 40 times 6 times 2 when it's in the VGA sync generator for reasons we'll talk about some other time. But that's a weird number. When it's a power of 2, it can just put it all into a single OR gate or an AND gate and just get the answer direct without doing any math or a real comparison. All right? So, yeah. Text mode is the bane of our existence right now. but we're still not using too much of the LUTs, and I think we can get in the sprites with less than, 6,000 more or 5,500 more LUTs, and this thing should be successfully functional as a replacement for the TI99 on the Nouveau. Woo-hoo! So I'm not only overclocked. You could say I'm in extra innings on this one, but that's the way it is this day in the VDP99 development history. Thanks for watching. I'll see you next time.